啊，怎么加入啊？邀请只能邀请81，这个是这个是
啊，
吗？
81777啊，对，PPT 发你微信上，
发我微信上就新版嘛。但是我刚弄完那
你再
个，
改改，你再改改这个，
发我新版，然后那我只把那几页替换成我的呗。
可以啊。你把这个放桌面上面。
我这没有桌面，我这只能先放桌面上就行。
在电源。
对，我需要一个电源，我感觉我这撑不住这么久，如果要是一上午的话。
来，你给我看
我
看你的那个，
我有转接头，
你
我的
number 那
number
个
OK
Zoom link。
8177，然后下面应该有个密码，你输了之后467723。
只有这种，
我有转接头，没问题。
那你拿转接头先给我这个电源。
我有电源。
好，你把声音关了。但现在这里就是哦，关注。
这个麦应该是不是关掉？他刚才说是不是应该关掉？
So let's move on to the second part, where we will explore the potential of different AI technology in addressing complex network problems. So in this part, we will cover four kinds of technology. That's graph embedding and graph neural network, and deep reinforcement learning, and also the physical reinforcement machine learning. And finally, we'll talk about a generative model and large language models. So first, graph embedding. So as we described before, that we think one distinct feature between complex network and also we call it simple network is that high order interactions are very important in these kind of scenarios. So we think that when using this technique to deal with complex network problems, high order interaction are very important to consider when we're doing the when we're doing this kind of research. So we know that for a graph embedding, it can using some sampling technique to extract the high order in structures and then to obtain the embedding through some neural network structures. And by combining with graph neural network, it will has use more deep or more dense network structure, and it can more easily capture the nonlinear relationship in these kind of scenarios. And there is an example in that's NIPS 2019 paper, which firstly used the hyperbolic space to capture the high order interactions in this in network science. And we think that is a very typical example of how we can design graph neural network that can map a complex network into a new hyperbolic space. And compare with some traditional methods, these data-driven methods, they are more more flexible when some a real-world situation where a theory cannot be analytically derived. And the second technique we think are important is a deep reinforcement learning. We know that RL is a specialized AI paradigm that can solve high-dimensional Bellman equation systems, and it can enabling effective decision-making and optimization across complex networks. And so let's take an example. So in this example, in the author in this paper, they derive an RL plus GM-based model that can design a complex network used in urban scenario, which is the community structured planning. We know that when we plan a city, we have to think about the relationship between different road segments and also the functioning of different spatial rooms. But when we structure this as a network, we can use the network science technique with also the data-driven RL-based method to solve this high-dimensional problem that cannot be easily solved by traditional method. And in this paper, they use this technique to they can efficiently generate different community structures given different objectives. And the third one is what we call the physical reinforcement machine learning. We know that in complex systems, that many physical knowledge exists in different systems. And by using PIML, we can integrating the physical laws and also dynamic into the a deep neural network. And it can not only improve the prediction accuracy, but also the interpretability with kind of limited data. And in this in this scenario, the normally used we can for example, since in real world network, the geometry of this network are very important. So we can use some geometry deep learning method to design the graph neural network. And we can also apply some physical-based loss function to add the constraint on the neural network. And finally, we can also employ some continuous time framework to simulate the system evolution. And so in this example, the author of this paper, they proposed a physical informed model that can simulate the crowd movement. So when we consider the crowd movement in a dance scenario, we can consider each person as a node, and the interaction between these people becomes an edge. And so by considering this as a graph, we can more easily to categorize the interaction between them when they're moving through the space. And actually, in this scenario, there's a very interesting physical-based model called social force that is motivated by the Newton force formula that and it considers the human movement as two kinds of force. One is the attraction force that will attract you to the destination, and the second is the impulsive force that will move you to avoid from a collision between people. So in this paper, the author combined this kind of physical neural network to more realistically simulate the crowd movement in a dance scenario. And the final technique we think that are highly potential for a complex network problem is a generative model and a large language model. Basically, they're all generative model, and they're all performs well at learning the complex distribution from the empirical data. So they can produce realistic samples by capturing the nonlinear relationship and intricate pattern within real-world networks. And for a deep generative model, it already shows advanced pattern distribution modeling across diverse network domains beyond traditional rule-based method. And for LLM, it also exhibits human-like ability across diverse tasks. So in this example, authors, they proposed the score-based generative modeling method to design a protein. They consider the protein structure as a graph, and then use the diffusion-based model or the score-based model to generate the complex structure of protein in very short seconds, and to will capture the complex distribution of this kind of data. And for the LLM, it can empower the combinatorial optimization methods, such as the evolutionary algorithm, to address the very hard problems in network science. There is a very famous work last year called FunSearch. It used the LLM with evolutionary algorithm that can solve the very hard to solve mathematical problem by using LLM to analyze analyze the EA algorithms, EA performance, and then to improve the original prompt, and then by constantly improve the prompt to solve this problem, then it can generate a novel program of solving this hard situation. And so motivated by this kind of fund search, there is a recent work also in last year. They utilize the LLM-empowered evolutionary algorithm to address the critical node detection problem in a complex network. It will also consider this problem as a combinatorial optimization, and then use the LLM to optimize or to improve the original algorithm, which can also formalized into a series of program code, and then use LLM to analyze the previous performance, and then to update the prompt to improve the code, and then it derives some novel solution to this important problem. So in summary, we think that AI offers powerful tools such as graph embedding to extract the high order structure in networks, and also it can use RL for decision making and physics informed machine learning for node data modeling, and also generative model for creation. And each will contribute uniquely to advancing complex network science. So now in part 3, we will categorize several key research problems in this field, and we will look at different challenges and how AI will tailor to each kind of problem. There are 6 kind of important research problem, we think. First is a representation problem, how to represent a complex network in a continuous space. And so we can do downstreaming task. And the second is the prediction, how to predict the non-trivial patterns on the network in both node level, edge level, and also the graph level. And the third one is simulation, how we can simulate the dynamic process evolve around through the temporal dimension. And the fourth one is the inference problem. Given empirical data observed from a real-world network, how can we inference such as the topology or the dynamics in the network? And also, and the fifth one is the generation problem, and how we can generate a different kind of network using the AI method. And the final one is the decision-making problem, how we can control a network or dismantling a network. And so next, another speaker will bring us to the introduction of this part.
Okay. So hello. First, the representation learning is a foundation of network analysis, and classic methods like deep work and node-to-vec change the game by converting nodes into vectors. Think of deep work as taking random walks on the network. Nodes that appear together in this walk get similar embeddings, and node-to-vec builds on this, letting us adjust how far we jump between nodes. And it's great for capturing both local and distant relationships. These techniques are simple but powerful, and forming the basis for so many downstream tasks. But networks are more than just pairs of nodes. High-order interactions like 3 or more nodes interacting, or subgraph structures like common motifs and temporal dynamics. It is how networks changes over time. They add layers of complexity. And for high order, we've seen hypergraphs and symplectical complex. And for subgraphs, motifs like triangles in social networks. And for time, models that incorporate past states. And the key here is that traditional methods fall short, and we need AI to handle this nonsense. And real-world networks are full of high-order interactions. And think of a protein complex needing 3 proteins to function, or a group project with multiple co-authors. And standard graphs cannot model this, and because each edge only connects 2 nodes, and that's where hypergraphs come in. A single hypergraph can connect 3 or more a hyper-edge can connect 3 or more nodes and capturing this multi-entity interactions. And this is crucial because these high-order structures deeply affect how networks behave. Let's clarify the difference. A regular graph has one hyperlinks, and that is a pairwise edge. But a hypergraph can have two plus hyperlinks. For example, a hyperedge connecting nodes A, B, and C, and a symplectical complex goes further with one complex, two complex, etc. And these structures better represent the real systems, but they are harder to model. And the goal is the goal is to adapt machine learning to understand these complex topologies, not just simple edges. So how do we learn from hypergraphs and simplex? And for a hypergraph, methods like hypergram adapt random walks to traverse hyperedges, while HGNN extends message passing to hypernodes. And for simplexes, simplexes, simplex to vec and Hodge-Lab use algebraic topology to capture multi-dimensional relationships. And the takeaway is we no longer limited to pairs, and AI can now handle the rich and complex interactions that define real-world systems. Moreover, motifs are frequent subgraph patterns, like a triangle in a social network. For example, A connects to B and C, who are also connected, and these are not random. Real worlds have way more motifs than random ones. So motifs encode hidden high-order relationships. For example, a triangle might represent trust between 3 users, and capturing this helps us understand network behavior at a deeper level. But defining the hyperedges can be tricky, and especially when data is pairwise, for example, like friend edge in social networks. But motifs can offer as a workaround. Even with pairwise data, we can identify common subgraphs, for example, triangles and 4-node substructures, and use them as proxies for high-order interactions. And this keeps things simple while still capturing complex dependencies, and it's perfect for networks where explicit high-order data is hard to get. So here is how it works. So first, we should find all motifs in the network, and then build a matrix of how nodes co-occur in these motifs. For example, HONE published in WSDM 2020, they use low-rank decomposition on this matrix between nodes through their motif connections. And this method let us incorporate high-order patterns into traditional graph learning and bridging the gap between simple edges and complex structures. So networks are also not static. Think of brain networks with evolving neural connections or ecosystem with changing species interactions. Temporal representation learning need to capture how nodes and edges change. So the challenge is handling high frequency data, long-term trends, and sudden shifts. But we can't just ignore time dynamics, because they are central to understanding the system. There are also methods to handle these issues. For example, MSTN and Trend tackle this by feeding multiple time snapshots into GNNs and letting the model learn time invariant embeddings. SpikeNet takes a different approach. Inspired by neural dynamics, it uses an integrate and fine model where GNN outputs as forces driving state changes. This is efficient for large networks, reducing parameters while capturing temporal patterns. And for the future directions, we need to merge high order and temporal modeling, and imagine a hypergraph that changes over time, like a group project evolving with new members and interactions. And existing works like HNN and etc. lay the groundwork, but integrating this aspect is still an open challenge. So to recap, we start with static pairwise networks using a walk-based method, and then move to high-order structures with hypergraphs and motifs. And finally address temporal dynamics. And the key evolution is from simple static models to one that capture complexity, high-order interaction, subgraphs, and time. And this sets the stage for all downstream tasks from prediction to control. So the next one is a prediction problem. The prediction in complex networks happen at 3 levels. First is the node level. It means that we predict features like a user interest. And the link level, we need to find some missing interaction like protein interactions, or we want to do some knowledge completion. And for the network level, we want to forecast the collective behavior such as disease outbreaks, and these 3 use different inputs. For example, the topology, partial or full node features, and even dynamics. And they require tailored AI approaches. So considering for predicting prediction tasks on nodes, and we use OD node example. So for example, for social networks, users they are treated as nodes. They from different countries, users of different countries have different structural features. For example, age density and degree distribution. And another example is the citation network. For papers before 2015 and after 2017, they may have different content, topic, and different citation patterns. The authors in this paper, they construct the energy function of each node based on GN classifier, and the lower energy score indicates an in-distribution node, and otherwise they are out of distribution nodes. And they also exploit energy belief propagation to make that the energy score tends to the average value of neighboring nodes, and such that it amplifies the energy gap between the in-distribution and out-of-distribution samples. So for link prediction, the traditional method is in this field, they really relies on network theory, and for example, preferential attachment, but it is struggled with the sparse data. And for AI-driven solutions like GNNs, we can leverage rich node features and topology, and to improve the accuracy. For example, we take the protein-protein interactions task. This task aims to predict unknown protein interactions using observed interactions. For traditional approaches, they use pairwise prediction by using biological similarities between protein pairs. But however, the predictive ability of such method is largely influenced by these features. But we can fortunately, we can predict the interactions in the network perspective. We can exploit entire structural information and contain topological similarities implicitly. Moreover, the biological similarities can also be used as the link weights of the network to facilitate the prediction task. For example, the authors of this paper employs evolutionary neural network based on regularized Laplacian kernel. The first step is they train a deep neural network using a sparsely disconnected training network to obtain an involved and more complete network. The second step is that they use the evolved network as the transition matrix of the regularized Laplacian kernel, which is applied to predict the protein-protein interactions of node pairs that do not have direct connections. So the next task is to predict network collective behaviors, like whether a network will collapse under attack, and it requires capturing emergent properties, that is, behaviors that arise from interaction but aren't evident in individual nodes. In this task, AI excels by integrating topology features and dynamics into models that simulate these emergent effects. Using fMRI data, the author of these papers models the brain as a network of regions connected by white matter, and they use GNNs to learn node-level representations, which are then poured to get a network-level embedding. And this embedding let us distinguish diseased brains from healthy brains, showing the network topology encodes functional differences. And it's a powerful application of graph learning in the healthcare. And resilience. Resilience means whether nodal states consistently converge to unique desired stable state, and intuitively is whether a network bounces back from perturbations and it's modeled represented by a binary variable y indicates resilience, resilient network or non-resilient network. And using the authors of this paper breaks down the resilience prediction task into two parts, and a GNN for topology encoding and a transformer for temporal trajectories. By fusing these two parts of information, it predicts network resilience even when interaction dynamics are unknown. And this data-driven approach handles the high dimensionality and noise common in real networks, proving that AI can infer complex behaviors from limited observations. From detecting OD nodes to forecasting network collapse, prediction tasks rely on capturing scale-specific features. And transformers and the ENNs are our Armin techniques here, but challenges like predicting across scales or handling complex, completely unseen network types still remains. The next part is for simulation, and simulation let us to test what if scenarios, and for example, how will a virus spread if we block certain ages. And AI can improve simulation by completely learning from data and eliminating the need for strict prior knowledge and speeding up computations and adapting to challenging conditions. And for example, this paper named Neural Dynamics of Complex Networks uses neural networks to approximate dynamics, and even when the underlying equations are unknown, and it maps the observed time series to the hidden space and learn the dynamics from this hidden space and then map it back from the observation space. So it's trained to minimize the difference between predicted and real trajectories working for any topology. For example, grid, power law, and etc. And this is an breakthrough step for this field. And another work about learning neural contingent dynamics takes a further step, and it employs observed time series and the topology of the network to learn the contingent dynamics to simulate disease spread without assuming any specific model. And it outperforms traditional methods like VR, and especially when the network topology is dynamic or noisy. And this is also critical for real-time applications like predicting COVID-19 spread on evolving contact networks. Moreover, large networks are computationally heavy, so we simplify them into skeletons. For example, we grouping nodes into supernodes that capture the key dynamics, and such process reduce the complexity while preserving essential behavior, making long-term simulations feasible. Different dynamics, for example, oscillators and diffusion process require different skeletons, showing the importance of tailoring simplifications of the problem. So the same network from this results, the same network can have different skeletons depending on the dynamics we are simulating. For example, a power law network might have a skeleton optimized for castle failures versus information spread using hyperbolic imbalance. The authors identifies these critical supernodes, ensuring the simulations are both efficient and accurate. So in physics, particle interactions form complex networks, and graph networks model each particle as a node, interaction as edges, and use message passing to update states. And this captures both local and global effects, making it suitable for simulations like fluid dynamics or granular materials, showing the versatility of graph-based AI beyond traditional networks. When environment changes abruptly, for example, a new policy altering social network interactions, the authors of this paper use a shared ODEs with environment encoders, and they also use a contrastive learning to help the model distinguish between different environments, ensuring it can generalize to uncertain conditions. And this is also the key for adapt systems that need to react sudden changes. For gradual changes like urban traffic patterns evolving over days, the authors of this paper use context variables and graph ODEs to update connections dynamically, and this adapt to slow environmental shifts, ensuring the simulations stay accurate without retraining from scratch. And it is critical for long-term forecasting in domains like urban planning. So AI-driven simulation is data efficient, fast, and adaptive. And these three traits that traditional methods struggle to combine. But whether learning dynamics from scratch, simply in simplifying large networks or adapting to change, these techniques open the door to realistic scalable simulations of complex systems. And the next part is inference. Inference is about reverse engineering networks using node trajectories to infer hidden topology or dynamics. And this is crucial for systems we can't directly observe, like gene regulatory networks or underground criminal networks. So without knowing the true topology, and the authors of this paper feed dynamics equations to data and construct a surrogate topology from interaction terms. And this approximate real connections, even if it is not identical, but it still works surprisingly well for predictions dynamics, proving that we don't always need ground truth to model the behavior of the entire system. Moreover, in oscillator networks, for example, rhythms, circadian rhythm in cells, connections may changes over time, and data-driven methods can infer these dynamic links even in noisy conditions by modeling frequency and coupling strengths. And this helps us understand synchronization phenomena in biology, physics, and beyond. Moreover, using binary time series, for example, whether a node is active, we can reconstruct symplectical complex, identifying two complexes or triangles that represent three-mode interactions. This statistical approach uncovers hidden community structures or functional modules that pairwise data alone cannot reveal. by applying machine learning to historical data. And the authors of this paper can reverse engineer how networks evolve by identifying key events like community formation or critical link additions. And this is also invaluable for understanding the origins of complex systems from ecosystem to urban infrastructure. And dynamics inference combines topology and node states to model how systems evolve. And the core equation includes self-dynamics and integration dynamics. Unraveling these components when both topology and equations when both topology and equation are unknown, is really important problem. So for the network dynamic inferences, there are mainly three paradigms. For the library-based method, they use sparse regression to select key terms from a predefined function library. They blending domain knowledge with data. And neural network based methods like Lagina use neural networks to approximate dynamics and then derive symbolic formulas for interpretability. And each has this is placed for libraries for interpretability and neural networks for high dimensional complexity. So a paper published in Nature Computational Science, the authors first generates candidate functions for self and interaction dynamics, and then use sparse. Okay, they use sparse regression to select the most important ones, and this reduces model complexity and ensures physical interpretability, making it ideal for systems where prior knowledge exists but needs data-driven refinement. And another work, for example, Lagina, they trained neural networks to approximate dynamics, then apply symbolic regression to convert these approximations into interpretable equations. And this they also incorporate diffusion term to discover the stochastic differential equations of the system. And this bridges the gap between black box AI and physics based models and offers both accuracy and insight. And inference is about, for conclusion, inference is about uncovering the why behind network behavior, whether it's hidden topology and unmodeled dynamics or evolutionary history. By combining data-driven learning with physics-informed techniques, and we can infer a complex mechanism that were once out of reach. So the next speaker will share the generate and design of networks. Okay.
For generation and design of networks, normally when we want to generate a network from scratch, we will have some, I think we will have some real world applications. So the problem is formulated as that given some specific conditions, we will generate new network that are similar to the reference network, but also has some good property. For example, like in drug design or in other scenarios. So in this problem, we will want the network to have both realistic characteristic compared with reference network, but also some improved property compared with the reference networks. And another problem we think is kind of similar to the generation, but we think it's called the design problem that more application oriented. And in this scenario, we will given a network and also the constraint we want this network to exhibit, and then we'll combine them to generate the new networks. First, an example of the generation of network is we think an important application is that we can do the data augmentation. So in many problems, especially in the graph machine learning problems, the examples are kind of sparse, and we have to train our model on some unlimited data scenario, and this will cause our model to suffer from limited generalization capability or other issues. So in this work, authors they deal with a problem called resilience prediction. That means they want to, given a network, they want to predict whether this network is resilient. And resilient is a kind of capability, especially in real-world ecological systems. That means whether the system can recover from external perturbations. So by this means, we can easily find that we are very difficult to find enough samples for training a resilience prediction model, because we have to observe a real world ecological system and then to find out whether it is a resilience or not. So in this paper, authors, they propose a generative technique to generate many similar network samples that can help them build a more powerful prediction model. So the generation problem is formulated as given the some real-world example, they want to generate both the network topology and also the network dynamic on the jointly. So the framework is divided into 3 stages. So first, they were pre-training a diffusion-based model that can generate the nodes and edge, and is supervised by a cross-entropy loss. And to generate the dynamic on the graph or on the networks, they use a neural ODE to simulate the temporal evolution on this network. And then we all know that a diffusion-based model has a capability of called classifier guidance that can help the guide the generated network to have some specific property. So authors they use this classifier guidance to generate a specific kind of network that can have the property of resilience. And then by using this generative technique, they generate many augmented samples that can help them to train a more robust resilience predictor. And as for the design of network, this example, they focus on the protein design of real-world natural networks. And we design the protein structure with a given property and function can be formulated as a network generation problem. And they also use the score-based method to generate several parameter matrix. And then they were based on this matrix, they will synthesize the 3D protein structure with constraints of the generated parameter matrix. And in this problem, the network refers to the interaction between the amino acids between them, because if then they're close to each other, then also will add an edge on this network. And another example is also about the protein design, which is to generate the amino acid sequence based on 3D structure and functional features of proteins. And so in this method, they also treat the this kind of sequence generation as a language modeling. And they use the GNN to model non and dependencies of amino acids. and then use the network to generate amino acid sequence autoregressively. And another example is about a molecular conformation design. That is given a network or representation of molecules and also the node feature, edge feature, and atom coordinates. A better structure that will have more optimal energy landscape. So the target is to find a conformation that with a minimal energy. And to deal with this problem, they design a physical informed neural network to add some inductive bias, which is a 2-atom distance model and also the 3-atom bound angle model. All these are based on the physical knowledge, and by integrating with this kind of inductive bias, they can their model can be more robust, especially in a limited data scenario. And the final example of the network design is the community network planning. In this work, authors, they want to design land use attributes and also the road layout of different plots in the urban community network. And so the method they use is deep reinforcement learning plus graph neural network. In their problem formulation, they will model the diverse urban topology as complex networks and will formulate the planning problem as a sequential decision-making process on the network. And so in this, so first they will select the plot, then select the edge, and the road selection is is equal to the node selection on this graph. And this is a similar example. I think it's the same authors. They transfer this method into another new problem, which is they want to design the road network for slums. We know that for in some underdeveloped countries, slums are very normally existed in their cities, and to build a road network for this specific area is very helpful and social good. So they design this problem as also as a graph design problem, and they will model the diverse and irregular shapes of slums as the complex network, and then model the importance of different edge with graph neural network, and then use the reinforcement learning to obtain the optimal road network structure on given a specific plan. So for the generation and design of network, we have seen the AI technologies such as diffusion-based model, energy-based model, and reinforcement learning. They can be used to serve as a data augmentation for limited data problem, and also can generate some biomolecular structures, and also can be used in urban scenarios that can be serve as a planning agent for urban planner. And the final problem we are discuss is the decision-making and control problem. That means the problem is formulated as based on the given network topology and node characteristics. We want to intervene in the node or edge to influence the behavior of the entire network. For example, sometimes in real-world systems, network can be disrupted or can suffer from some issues, and then we want to add some micro level interventions. For example, we can change some edge between some nodes, or we can add some signal on specific nodes, and then to drive the whole system into the desired states. So this is called the network control problem. And also we can dismantling a network. For example, if we want to design a new drug that can specifically useful for some health problems, and then we can design a network dismantling approach that can dismantle the PPI network between the specific virus and also the cell. So for the network control problem, traditional methods they are always favor the closed form solution. This work they deal with some a problem called a data-driven control problem. That means we do not know the exact form of formula regarding the system we deal with. So the author they proposed closed form solutions that can be obtained by solving a constraint minimization problem. But the limitation is that they rely on the linear assumption on the network dynamics, so they can derive some analytical solutions. However, these assumptions are normally does not match in the real world systems, so it can cause some issues, especially some in nonlinear problems, such as when we want to control the real world system like human brain or the power grids. And so in this more recent work, authors they propose a complex network dynamic control based on reinforcement learning and graph neural network. They're using the finite step prediction control to deal with partially observed dynamic process on complex network. So to deal with this problem, they formulate the node subset selection for intervention as a ranking problem, and it can be efficiently solved with reinforcement learning. And it also used a graph neural network to serve as the environment model that can help them to model the observed network's node features and also the dynamic interactions between them. And so then they can aid the policy search in the following steps. And this work they are target for more complex real-world scenarios, such as when we want to intervene the epidemic process in a city or in a spatial area. And this work they're using the neural ODE to generate the control actions. The motivation is that we know that real-world network they often follow some continuous time dynamic process. So ODE are very suitable for deal with this kind of modeling. And given enough observation of the network evolution, they can train a neural ODE to simulate the dynamic process of this network, and then they can use the this ODE to generate the control signal with no energy. And these methods are targeted for real-world situations, such as when we want to control a power grid or other kind of man-made systems. And as for the network dismantling, we know that the problem is formulated as finding the key players in complex network, that when we remove these nodes from the network, the functionality or the connection of this network will be impacted very much. And so the problem is how to identify the critical nodes in these high dimensional networks. And usually there is a metric called accumulated normalization connectivity, which is ANC. And so in this paper, they use RL deep RL to solve this high dimensionality decision-making problem. So the goal is to find the nodes that can disrupt the network most quickly. So the reward is defined as the decrease of ANC after dismantling the specific code, a specific node. And the model they use are the combination of the GraphSage, which is a GNN, and also the deep Q-learning, DQN. And then they combine this together to solve this problem. And the one interesting thing of this work is that we all know that the real world network case are the sample are very hard to obtain. So the authors, they propose to first train their model on the synthetic network that can be generated in a manner without any limitation. And after they train enough samples on this synthetic network, they can transfer their model into a real-world network that is not only more complex, but also more high dimensional. And they find that the transferability of their model are fairly well. And so they can remove the nodes identified by RL effectively, and which can disrupt the network connectivity. So to summarize, in this decision-making and control problem, the main AI technology is includes deep RL and also the graph embedding of GNN. And also, if the network exhibits some physical knowledge, we can use PIML to solve this issue. And so by using this technique, the network control and network dismantling problem can be easily solved. And we have now can introduce both the potential of AI technology and 6 typical research problems for using AI for in complex network science problems. So now we are about to come into the coffee break, and after the coffee break, we will discuss the application that is when we're using the AI for complex network problems, covering both natural world network and also the man-made systems. And if there are any questions, we can discuss right now. And if not any questions, we can go straight for the coffee break. Thank you.
Good.
Yes.
Question.
Sure.
Yeah. Regarding the in-play finding.
Okay.
Normally, random walk with respect or PageRank was the very, very powerful tool for doing that.
You mean doing the finding key player?
Key player,
right.
So have you compared your approach with the PageRank or random walk with respect?
I think in this scenario, a very famous traditional metric is they just use the degree centrality. That is, for network, if we dismantle network choosing the node with high degree, then the connectivity of this network will down a lot. And that's actually that's a finding about 20 years ago. That is, they find that for some network, especially the power law network, scale-free network, that means the degree distribution of the network will follow the power law distribution. If we dismantle or this network follow the degree-based metric, then the network will suffer a lot. But for random network, as you mentioned, this kind of technique is not useful.
But you didn't compare.
I think in this paper, authors they compare with degree, and they are not our paper. They compare with the degree-based metric, but not using the PageRank, I think.
it is more sophisticated one, so I was curious about.
Yeah.
Yeah, another one is the hypograph.
Okay.
Have we tried with hypograph rather than graph? You mentioned that high order issues, right?
Yeah. In this paper, they only focus on the pairwise interaction.
That one. Yeah.
Uh.
Previously, you mentioned hypographs.
Yes.
It deals with the high order relationship, right?
Yeah,
With,
yes.
hyperedges, right?
Yeah. Yes.
So, but I think hyperedge can be modeled with a simple graph by using bipartite graphs, right?
Yes.
Yeah, but what is key difference with that? So hypograph modeling and modeling with bipartite graph.
Maybe Liu Chang, can you answer this question? Yes.
Hello. I think hypergraph may be the interactions between the involved nodes. Their interactions are not additive. For example, if you only use some pairwise if we use pairwise interactions, like multiple pairwise interactions, for example, a node receives interaction from two other nodes. These two kinds of interactions may be additive. They can use the sum, the impact of other two nodes, from other two nodes. We represent the total effect use a sum operation, but the hyperlink can jump beyond such sum operation, and they can model more complex in impact behaviors, I think. Okay.
After session.
Okay. So we are going to coffee break.
Thank you. Thank you for your nice talk. Yeah, you are. Yeah, yeah. Are you a professor? Yeah, after getting your PhD from. I see. I see. Oh, so now you join. Action one. The question was that the hypograph deals with the high order relationship, right? You know hypograph? I think. Basically, if we model the data, we have two choices. One, hypergraph. The other is bipartite graph model. Yeah, actually, the connectivity is similar, but as you said, the hypergraph deals with the relationship in shorter path, right? Because here, one mole is represented here, two moles, right? So that difference is the only thing. So I'm not sure about the result.
Yeah. I think I go on the context.
But many applications uses different. I'm not sure what actually I'm working on some applications with hypergraphs, but I'm not sure about its the power. Yeah, difference. Yeah.
And also, I think in some the biggest issue also they already do in I think
But yeah. Right away, why did you come back from industry? Do you want to be a professor? So after joining the industry, you think you are more or there are big salary difference in yes. How much? Those pounds were let's keep in touch if you join that meeting. I would have Hannah University, yeah, located in South. Yeah, email. Thank you. Thank you for discussions.
没法共享屏幕。
你可以那个它，它在哪儿啊？这个是吧？哦，这个。嗯，你让它 share 一下屏幕看看。
哎，现在应该可以了。OK，哎，我一直在说话呀。喂，可以听到吗？喂喂喂喂喂，诶，喂，可以听到吗？喂，现在可以吗？喂，可以听到吗？喂喂喂喂喂，现在可以听到吗？Hello Hello Hello Hello，
哦，我觉得可能如果是现
Hello Hello，
Check, check. 1, 2. So that's good.
Hello, testing, testing. Hello, hello. Can you hear me?我好像不是第一页。
Hello? Hello?
Hello, can you hear me? Hello, hello. Hello, everyone. My name is Yu Zhang, and I'm currently a postdoc at MIT. And in this section, I'm happy to share some interesting applications of AI in real-world complex networks. We will cover both human-made systems and natural systems. For human-made systems, we will introduce some interesting works on social networks and urban networks. For natural systems, we will cover biological networks and ecological networks. First, let's look at social networks, which tied closely with the web conference. In AI for complex social networks falls under 3 different categories. First, AI approaches are adopted to encode social networks with semantic representations or embeddings, which have a wide range of applications in social network prediction. Second, AI methods are leveraged to simulate the social network dynamics for revealing the underlying mechanisms of social networks. And last, the ultimate goal is to perform system control on real social networks based on the network representations. We will introduce several typical research works on all of these 3 different categories. The first application of representing social networks is dynamic link prediction, which is defined as estimating the likelihood of a future connection between 2 given nodes in a time-varying network based on the observed data. And this task is considered as one of the critical problems in network science, and it has been the foundation of various applications such as constructing knowledge base or building recommender systems. And in this link prediction task, there are temporal information characterizing the evolving dynamics of the network, as well as structure information which describe the network topology. And these 2 types of information are deeply interconnected in multiple scales. So there are microscopic nodes and edges, mesoscopic groups and communities, and also the microscopic level properties of the whole network, such as the degree distribution or the growth rate. And we know that microscopic temporal dynamics naturally emerge from microscopic temporal dynamics, and it also, in the opposite direction, influence low-level behaviors. Here we introduce a method named Attentional Multiscale Co-Evolving Network, or AMCNet. It consists of 2 key components: multiscale representation learning module. This module learns embeddings that capture the structure information of different scales within the network. Microscopic level, the model adopts graph attention network to learn node representations for each snapshot. And in the mesoscopic level, AMCNet enhances the representation by introducing motif-based local pooling. And these motif-based graphs are constructed, and mesoscopic representations are obtained by performing weighted pooling on the learned microscopic representations. And for the microscopic level, a global pooling method is used to encode the entire graph information. And the second key opponent is multi-scale co-evolving attention module. This module is designed to build connections among temporal dynamics of these different structure scales and learn their complex evolving dynamics. And this model employs a sequence-to-sequence module, which is an encoder-decoder framework with LSTM blocks as backbone to learn the evolving dynamics of each structure scale simultaneously. And it also incorporates a hierarchical attention-based mechanism as the co-evolving attention mechanism to build connections between the learning process of different scales by using higher scale representations to guide the learning process of the lower scale representations. And finally, these representations from different structure scales are jointly leveraged to predict future links between 2 nodes. And the empirical evaluation on the YouTube dataset can show that they can predict the next 9 time steps performance, the performance of AMCNet outperform state-of-the-art baselines, and it remains stable as time goes by, which suggests a very good generalizability along the temporal dimension. And it also consistently outperform the baselines in multi-step dynamic link prediction task across 4 different data sets. And in the meantime, we conduct a population study on the mesoscopic motifs, and they are found to be the most informative, particularly the 3-node motifs, while we also observe marginal effect of adding motifs with more nodes. Now is the second step is simulating social network. Social network simulation involves modeling and predicting human behavior, such as opinion formation and propagation within time-varying networks. And this will utilize theoretical models, often expressed as equations or agent-based simulations, to describe social interactions and understand their impact on the evolution of opinions and collective phenomena. And the goal is frequently to create believable computational processes of human behavior to study, test, and prototype social systems in simulated environments. And two examples of work in this area employ neural ODE and large language model. In the first KDD paper, the social science theoretical models are reformulated as ordinary differential equations, which become constraints on the neural network. And they are integrated with large amounts of social media data and site information to predict the evolution of individuals' opinions in social networks. Also, the second one is the Stanford AI Tong that extends a large language model to simulate believable human behavior in interactive environments by storing experiences, synthesizing high-level reflections, and dynamically retrieving memories to plan behavior. So this is a social network simulation system, or the S3 system. So at the heart of social simulation lies two perspectives: the dynamic feedback or interaction among individuals and the states of the population. In S3, we leverage the human-like capabilities of LLMs in sensing, reasoning, and behaving to construct this simulation system. And the system uses real-world social network data to establish an environment, while we also, the fine-tuning and prompt engineering techniques are also employed to ensure the authenticity of the agent's behavior within this environment. And this S3 system supports simulation at both individual level and population level. At the individual level, it simulates three aspects of user behavior: emotion, attitude, and interaction behavior, such as forwarding content, creating new content, or remaining inactive. This simulation considers factors like user demographics inferred from data, memory of historical content, and the informational environment. At the population level, the system captures the emerging collective behavior that arises from individual actions and internal state changes. This includes simulating the propagation of information, attitudes, and emotions through the network. And by integrating LLM-empowered agents following the agent-based paradigm and leveraging real-world data, S3 provide a powerful tool for researchers and policymakers to gain profound insights into intricate social dynamics, and also facilitate informed decision-making and address various societal challenges. And we evaluate these S3 system, this LLM agent-driven social network simulation system on real-world data. And we demonstrate this promising accuracy at both individual level and population level simulations. And we can find that the LLM agents, they accurately forecast the propagation patterns of two controversial events on social medias. And the results near perfectly feeds the ground truth data on how this information propagate on the social media. And for controlling social networks, we will introduce one application of attacking a criminal network to achieve the fastest dismantling. And so here we aim to remove the least number of nodes such that the word dismantles into disconnected different parts. And it is known as an NP-hard problem, which also features an enormous solution space. And since we have a budget on node removal, so we also need to conduct a trade-off between effectiveness and efficiency. So here, these finder method utilize deep reinforcement learning to perform efficient search of critical nodes. So a method called a deep Q network is employed to estimate the value of each node and also sample the node removal actions instead of enumerating all possible solutions to address this NP hardness problem. And we can see some empirical evaluation on real-world criminal networks. You can see that the finder approach leverage reinforcement learning, which can dismantle criminal networks with very low cost. And we can also visualize the identified key players, which are largely ignored by baseline heuristic methods. And the previous Vandermeisser only considers the topology of the network, but for some real-world social networks, such as how rumors or informations propagate, we have not only the topology structures, but also the information dynamics or opinion dynamics on how this information pass between neighbors. So here, introduce a method. Our method to have this application in rumor mitigation in social networks. So here we utilize graph neural networks to unify topological and dynamical features and perform message passing and neighbor aggregation to learn informative node and edge representations that take both topology and dynamics into consideration. And we search mitigation strategies, which are the edges to be blocked with reinforcement learning. So here we evaluate this method on real-world social networks, and we can find that these reinforcement learning combined with graph neural networks can achieve over 37% reduction in rumor spread by blocking only 10% of the edges, and it outperforms all existing heuristic methods and machine learning-based methods. And here we will leave some future directions in the AI for social networks domain. First, most of the words only consider the cooperative relationship in the social networks, but in real-world network, there can be computations or some non-linearity. For example, here in the networks of different couples, there definitely exists some computations. And another future direction is to consider these complex interactions between nodes, which usually feature some unknown dynamics. So if we look at the opinion dynamics on how it exchanges between neighbors, it is unclear whether this dynamic is linear, hyperbolic, or in other forms. And real-world data also contains very large amount of noises. Also, if we also the network also shows some complexity and heterogeneity of human behavior. And if we extend the pairwise relationship to higher order structures like motifs, then there are definitely some higher order effects between like 3 or more nodes, which can generate more fruitful results. And the second human-made system we'll introduce is urban networks. So there are basically two categories of urban networks. First are the mobility networks generated by human movement within the city. And the second category is the infrastructure networks of the cities, which can be the road networks, land use networks, or water or power grid, these networks. And for all this network, there exist three different types of tasks that AI can play a very critical role in, which are prediction, generation, and optimization. For urban network prediction, here we introduce a work that utilizes graph neural network to on the road networks. So here the road junctions become the nodes of the graph, and road segments are the edges of the graph. And here this work utilizes graph neural network to learn representations for urban road networks. And the intra and intercity road network homogeneity can help us to understand some growth patterns of the city, such as the spatial equality of human terrain assistance, and also the cross-city policy similarity. And for the generation, the very first work is this FlowGen method, which utilize generative adversarial networks or GAN network to generate this flow. So it has graph neural networks as the discriminator, which consists of three parts, which the first one is permutation invariant flow pooling, and the second is in-out flow bidirectional node method passing. And last one is attentional based readout to first generate the adjacency matrix, then generate the specific value of this OD flow. And on the real-world taxi trips data, we can see that this FlowGen method can generate accurate and also diverse urban flow networks. And in the last 2 years, the Fury model has shown to be outperforming the previous generation of GAN models in image generation. And we here also find that we can utilize this diffuser framework to replace the previous GAN model in generating urban origin destination flow. And we evaluate on real-world OD flow data, and we can see that the diffuser model also outperformed GAN on OD flow generation, and the improvements can be exceeding 30.9%. And the last one is urban network optimization. So here we focus on one specific case of urban metro network design. So here we first construct a multi-graph graph neural network state encoder to extract both geographical information and transportation demands. So the spatial, we have introduced two types of address. The first one indicates the spatial contiguity between different urban regions. And the second one indicates the regions that has very large urban flows. And then we employ a policy network to select the regions for a metro network expansion, and value network to estimate the planning effect. So by combining the graph neural network and reinforcement learning, we can see that it's substantially improved the satisfied OD flow by over 15.9% under all different budgets of metro network expansion. And another very classical urban network optimization task is facility location. So here we need to relocate the locations of different urban basic services to maximize the accessibility of these services from residents living in all different regions. So here, this is a very classical combinatorial optimization problem, which have very large number of baselines featuring optimization solvers. So here we propose a knowledge-informed reinforcement learning method that incorporates rich prior knowledge into the model design as inductive bias. And we further extend the framework with divide and conquer algorithm to make it able to address both single facility location and multiple facility location. And we can see that the knowledge-informed reinforcement learning can improve facility accessibility by about 40%, and it can accelerate solution generation by around 1,000 times. And then I will briefly introduce some applications in natural systems, both biological networks and ecological networks. Biological networks describe the complex relationships among entities within biological systems. And the entities can be genes, proteins, cells, and molecules, etc. And the relationships are thus chemical reactions or biological interactions between these entities. For example, here we have the protein structure networks and the gene regulatory network. In AI for biology networks, typically have can play three roles in this domain. First is mechanistic understanding of the complex relationship between the structure and function of biological networks. For example, there works using 3D CNN to perform protein functional site detection. And we can also to perform representation learning of protein sequences using LSTM. And the second category is simulation and prediction of dynamical process and network evolution within biological networks. And one example is the famous AlphaFold work, which predict the protein structure from amino acid sequence with physics-informed deep learning. And then the last category is optimization and control of variables in biological networks. For example, we can use reinforcement learning to design protein structure. And here we introduce one specific example of protein-directed evolution. So here, these work first construct an amino acid knowledge graph, AAKG, to represent biochemical relationships among amino acids, and then utilize a protein language model to sample mutants through preferential random walks on the constructed amino acid knowledge graph as a policy network, and also has a fitness predictor as the reward model, and it is theoretically fine-tuned to provide accurate feedback. And on protein data sets, the evaluation shows that these no RLM models can more efficiently identify high fitness mutants than all existing baselines. And the second type of the natural systems are ecological networks, which describe the interactions among species within a biological community, such as predation, parasitism, cooperation, and other forms of interactions between species. And AI for ecological networks also has three different roles. First is very similar to the biological networks. First is mechanistic understanding of how species in mutualistic networks achieve coevolution through direct or indirect pathways. For example, can model complex interactions with graph neural networks or recurrent networks. Second is simulation and prediction of species interactions and ecological network evolution to uncover strong or weak connections between species and their impacts on network stability and evolution. And the last one is optimization and control of ecological management strategy. For example, deep reinforcement learning are adopted to promote biodiversity and achieve long-term ecosystem stability. So one example is a graph ODE method, which learned the continuous time ecological dynamics. So here, a graph neural network is utilized to generate the neural ordinary differential equations on ecological networks from observed time series on the network structure data. And by applying mutualistic dynamics on different kinds of topologies like random networks or power law networks, we can see that this graph ODE model can fit the ecological dynamics accurately on all kinds of different topological structures. And the last work I'll introduce is a recent work that can apply to both ecological and biological networks. And the task to tackle is network resilience prediction from observational data. So for both ecological and biological networks, if we impose perturbation on the node states, the network can be irreversibly transit to an undesired state that fails to recover from the original desired state, or it is resilient, it can quickly recover from the perturbation and keep as its highest or our desired level. So here, this resilience inference or ResInf model utilize deep learning to predict the network resilience from observed data, considering both topology and the dynamics. It utilized a transformer model to learn the node activity dynamics and utilize graph neural networks to learn the network topology. And if we run ResInf on both ecological and biology networks, we can see that it predicts network resilience accurately with over 40% progress on F1 score, and it can generalize to same topology, same dynamics. So that's all the work that I like to share on the application of AI for complex networks. Thank you.
Wait. Okay, great. So after introduction of the application of AI for complex network, I will go to the next part. Actually, we have another speaker online. He will join us about 10 minutes. So I will first skip to the open discussion part. So in today's tutorial, we have start from the background and the challenge for using AI technology in complex network science, and we'll have also reviewed some candidate AI technologies such as graph embedding, GNN, and deep reinforcement learning, and PI/ML, and generative models. And we have also identified 6 typical problems. That's representation, prediction, simulation, inference, generation, and control problem. And also, Zhenyu has discussed two kinds of application scenarios for using AI in complex systems. That's human-made systems like social network and urban network, and also natural system and biology or ecology network. And about 10 minutes afterwards, Professor Carlo will introduce an artificial neural network. That's how we can use a complex network for AI. And so I will skip to first open discussion part. So we think first, when we're using the AI technology in complex network problems, a very important open problem is that how we can balance between data and knowledge. We all know that there exists some physical knowledge in real-world systems, but how to integrate that into the AI methodology design. Actually, two kinds of paradigm are normally used. First is we can use some specifically designed neural network to add this physical knowledge, which is inductive bias information. And the second, we can add this information from the observational data. That is, we can synthetic some data by physical formula, and then use the data to train a model. Then this model, they intrinsically capable of handling this kind of physical knowledge. But how to balance between the model design part and the data sampling part is, we think, is a very kind of trade-off, and also it's the open problem to discuss. And the moreover, we think that we can kind of integrate these two things together. So given with the PI physical involved machine learning technique, we can integrate the knowledge into the data-driven model, and then this kind of model are better at handling the limited data problems. And then given the empirical data, we can also discover some new knowledge or new physical insight from the data that beyond the traditional theory. So maybe we can combine them together to get more complete understanding of the real world systems. And also the real world network, they have the multi-scale nature. That means sometimes we know we have complete knowledge at some certain scale, but at some another scale, we may have unknown mechanism. We do not understand the intricate process behind this scale. So for this, for unclear scale, maybe we can use the data-driven modeling. And for the knowledgeable scales, maybe we can use the physical-based modeling and combine them together to have a better understanding of the real-world system. And also, we in recent year, we see the rising trend of utilizing foundation model to handle real-world problems. And however, in complex networks, currently they are rather limited foundation model practice. And is there a universal physical knowledge that can enhance the foundation models' rapid adaptation and generalization across different domains? We think maybe we can obtain some insights from the graph foundation models. And also in our many of our discussed work in this tutorial, I think they follow a paradigm that is they can pre-train the model on synthetic data, which may be generated by mechanics models, and then adapting this pre-trained model to the empirical data, and they find the performance are really well. So I think this kind of transfer learning technique can be a starting point of the foundation model for complex networks, and also we can. So next we will wait Professor Carlo to join us in about 2 minutes, and we will set up the scenario. He's already online, so I will set up first.
Hello, can you hear me? Hello, can you hear me there? Can I have a confirmation that you can hear me inside the Zoom workplace, please? Okay, super. Then it is now come to share the slides. We can start the presentation. Mhm. Share. Okay, so I guess that you should be able to see the presentation, right? Can you give me confirmation, please? Hello? Is anybody there able to tell me if you see the slides, the screen? Okay. Okay, so we are 9:40, we can start with the presentation. And I worked also on the field of AI for complex network. I worked on algorithm for network geometry to map network in geometrical space. I invented the algorithm in this direction. And I still work on network geometry and network machine intelligence related with the AI for network science. But in reality, I entered in the field of complex system and network science because of my interest for the brain and for how the brain processes information. And this happens many years ago. And now I will give a story that can let you understand the path I made the research in complex system and network science and how this link to modern AI. So I should speak today of the content of these two articles. The first is an ICLR 2024 publication on network science for sparse deep learning and brain sparse efficient AI. And the second is a network electronics for neuromorphic dendritic network computation with silent synapses for visual motion perception. And this is network science for sparse neuromorphic learning, brain sparse efficient AI. But for reason of time, I will concentrate on the first part, and in the second part, I will give you just some hint. So if you go on my website, you will see that there is a quote. In this quote, I write, if physics studies the principles and the mechanism of the outside universe, brain science studies the principle and mechanism of the inside universe. My research is at the interface between these two disciplines. I deal with physics, engineering, or complexity and intelligence. And I study principle of natural artificial intelligence. And everything started in reality when I was a master student, and I should take a course in computer science at Politecnico Milano, but I was in love with the brain and the possibility of the brain to process information. And I asked to the dean of computer science meeting, I asked if the dean of the course of computer science some suggestions. And he told me, we are creating a new course where we put computer science and biomedical engineering together. And the new course aim to create the next generation scientists that are interdisciplinary and are able to build a new computer science based on bioengineering brain principles. And for this reason, I enrolled in this course. There was really a good chance for me because it was more than 20 years ago, but already I could formulate the questions of my entire career. Because in my opinion, if you are a scientist, the most important things are the questions. You need to identify questions that are fundamental and can change the way we create knowledge for the society. And for me, the first questions was clear when I started to finish the courses in this master. And actually, one of the main questions was why the brain can work with just less than 20 watts. And the professor in bioengineering were explaining the sparsity and morphology are fundamental for this ability to be efficient. But in that moment, we are speaking of around 2000, the field of neural network was focused only on fully connected network, and they were very expensive to the point that we could not really use. And my question was, as a master student, but why the computer scientists build this network fully connected? And the professor in bioengineering, in brain bioengineering, all the model we do on neuron network, all the type of model of neuron with noise, without noise, and morphology, and this one, they are all sparse, very sparse. The stress sparse is important. So this, it means we should contribute scientifically to artificial neural network, revolutionizing the mechanism and the paradigm. That was clear already as a master student. Criticize the society and the knowledge, the current knowledge, to create the next one. And when you are young, you are a revolutionary. You always think that we need to change this, we need to change the other one. And that was the right moment to generate my questions. And indeed, my dream was to start to modify this neural network and create artificial neural network that put inside this principle of sparsity and morphology. So the first question was, why is brain connectivity dynamically sparse? Because the professor of brain bioengineering were explaining the reality in the brain, the neural network have a synaptic turnover. This it means that some connectivity are removed because they are discovered not to be good for the training, and some emerge, new connectivity emerge. So it's the dynamic sparsity that is fundamental, not just static sparsity. And how to make a profit of this in artificial neural network? That was the first of my questions. Then I put these questions under the name of topology, because in my idea, I should study how the node connect, create a model of how the node connect, and the way mathematicians call this is a topology. And then the second point was morphology. Why morphology? Because in reality, as I told you, the neuron have a shape. The shape of the dendrite is fundamental for the processing. Indeed, we have the directionality in one direction or the other direction can create a different signal. And instead, in the artificial neural network, there was no any type of mechanism or type of design that was able to mirror this morphological problem. And then neuroglia, because the neuron are only a part of the brain tissue. The mechanism of learning in the brain are much more elegant, and you have a metaplasticity that is implemented by the glia. They feel how the neuron behave, and their network on network, and they modify the connectivity because they modulate it. And there is the third point on which my research is totally focused now. So I abandoned AI for network science, and I am creating network brain-inspired model for AI. This is my passion. And now let's go to understand what happened after I formulated these three important questions. It happens that if you want to have an idea what is a sparse network, my idea in that moment was to study how to dynamically change this connectivity. And therefore, I proposed a thesis to my professor in computational, master thesis. I proposed the idea to different professors to find a mentor to implement the first sparse training network. And the professor all rejected this idea. They told the neural network they don't work well, maybe they will never work. We do Wapping-Chervonesky theory, we do large margin classifier, receptor vector machine, random forest, statistical machine learning based on Lasso, logistic, statistics is the future in machine learning. And I thought, no, you don't convince me because you didn't give a proof to me that this technique don't work. A science is this one. And I'm very rigid with my mind. When things are logically not founded, the people don't convince me. So I thought I must work on that because there are no proof and evidence that are able to negate these conditions, to nullify them. And actually, there are strong evidence that in the brain sparsity, high sparsity, is together with morphology a fundamental tool. So I have more reason to believe than not believe. But the problem was how to shape this connectivity. I remind you that the first article, Olajuwon Barabasi, and the one before on the Watson-Strogatz model in 1998, they were just 2-3 years before my initial creation of these concepts. So it means I didn't have a way and even knowledge how I should model the sparsity and the connectivity. So I start to research myself. A long path of research was always as a teaching, doubting person and trying to find solution everywhere. For me, science is unique. There is no border. You just need to understand and go deep in that. And that's what I start to think. I do a PhD in network science and network biology because network biology is ready to understand how topology and connectivity have a function in gene, in protein, and so on. But the field of brain science is not still emerging well. And so I start to study the paradigm of how the network connects. And of course, my idea was to start from the brain, but there was missing knowledge on how to apply the concept of the brain. Because the quote of Webb, neurons that fire together, wire together, was always intended out changing the weights on a static connectivity, but not changing the connectivity itself. There was actually one of the principles that I learned that was fundamental to learn in brain, a real neural network. And so I give a name of how to learn by changing the connectivity and together with the weight. I call it epitopological learning. Why? Because it is learning by creating new topology. And this new topology come across the process of growth of the network. And I created also this term, complex network intelligence, to identify the knowledge that is related with network connectivity and how this influences functioning complex systems, in particular learning and intelligence. And then I understood that in network science, there was a field that studied how to predict the connectivity of the network in the future, giving the connectivity I have in a certain stage. And this is called the link prediction. Therefore, I thought I need to create very strong rule for link prediction. And when I will have that this rule works in general, I can put it inside my artificial neural network and create the first artificial neural network that learn with network science. Learn with network science the shape, the connectivity, how it evolved without gradient, without anything. Just the knowledge of how the connectivity is in this moment suggests, because of the shape, how it should be the next connectivity. And in that moment, in prediction, there was an idea. The idea was giving Mark Newman. It was that common neighbors are a fundamental item to predict the likelihood a new link arise. The idea is the more common neighbors I have, the higher is the likelihood to have interactions. And my interpretation of this was that it could be related with Debian learning, but was missing an important part. Because cohort of neurons that fire together, wire together, is cohort of people that speak each other, tend to connect. Cohort of protein that are functional interacting will bring to other interaction of between the protein that are in the complex dynamically. So my idea was, I need to change this paradigm from being common neighbors based to be local community based. And to be local community based, we need to make sure there exists a local community. Because if you have a local community, you have an ensemble of neurons, an ensemble of protein, an ensemble of people in the society, and so on, ecological species, they do a function in that ecosystem. And there it means that there is the rule of Hebb is not just particular, but is a general rule of complex system. It just had the idea in that domain, but it's valid everywhere. And therefore, the neural network, when apply a rule like that one, they are working like many other complex systems that evolve by changing the weight or the connectivity, and they tend to learn a connectivity. So I should now put this also in neural network. And the rule I created is very simple. It says that you need to minimize the external links to your common neighbors. The less they are, the higher is the likelihood that these two people or these two protons, these two neurons will fire together. Because this ensures that this is the critical mass, is the local community that is isolated for the rest and speak internally to create a function. And here is the simple index that explains the concept. This is the Cannistrà-Shebb rule 3. There are different rules, but this is the main rule. It says that you need to count your common neighbors by penalizing for your external links, because this ensures you have an energy barrier and the emergence of a local community, the force a function, and a connectivity between the members of the party. Then Lajo Barabasi, in 2019, in Network-Based Prediction of Protein Interaction, wrote the best performing literature method Cannistrà resource allocation out of 23 different methods. This was one of the methods I created at the beginning. Then I invented the edge theory that is more elegant and more finalized and formalized in the right way. And Tao Zhou tested on 137 real network of different type of system, complex system, and he concluded that overall speaking, the classical Cannistrà-Shebb index performed the best among all considered candidates. I had finally the rule of my dream. Simple, no parameter, physically based, concept explicit, so you can understand the meaning of what it's doing. And I was ready to put them in neural network. This is an article that if you want, you can read to have a history and a knowledge about all of that. And here we are. I applied also on protein interaction network, but I don't have time to speak this today. But I give evidence that we can predict much better than AlphaFold the connectivity of proteins without knowledge of anything except the previous knowledge of how the network works. So we cancel many protein interaction and we try to classify all the one missing using AlphaFold or using protein interaction prediction based on network science. We outperform way AlphaFold 3. But this is not the point. The point is what happened to that student that had that idea. That student arrived in Tsinghua. And when I arrived in Tsinghua, that was the moment to make the jump, to put back and prove to myself the 20 years of research, to find that deeply a rule that can predict in any complex system connectivity better than AI, because we perform in this moment better than even message passing graph neural network. I have evidence, we are submitting the article on that. A simple rule beat in this moment all AI for link prediction in complex network, I can assure you. And now we see what happened in neural network. The problem came out, a lot of parameter in neural network. How to solve the problem? Sparse AI chip developer raised tens of millions of dollars. Sparse network start to enter in the field. Here a first article. In 2010, scalable training artificial neural network with adaptive sparse connectivity inspired by network science. When I saw this article, I was shocked. I thought, oh my God, they understood my idea. But fortunately, it was not the case. They introduced an approach that started the network sparse with a model. So you create 1% sparsity, 10% sparsity. You train to learn the weights. You remove the weights with the lowest absolute value. And then you add the link. But pay attention, this is the crucial point. How to add the link? They added a random. So there is no really network science. They just use the network science to initialize the network, no more. But not for the evolution, to predict how new link should come out after I erase them. And Google came in the game. In 2020, Google DeepMind arrived to the conclusion that the gradient was a good information to predict which link to add. But pay attention, this is not a sparse string approach, it's a tricky. It's not true. There is a trick there. You use the information, all the metrics, because you use all the gradient, all the metrics. But in conclusion, they proposed the RIGGEL, and RIGGEL put the gradient-driven growth. And then I arrived finally. And my idea was just to use a simple rule, physical based, they can predict the next link using the model I proposed, the Cannistrati Hub. And here I call it epitopological learning growth, creating topology using the topology. And here you are, we improve significantly on different benchmark basic on MLP. This is a simple test against random. We always accelerate the learning because we have an oracle based on physics that can predict the new link that will come. But this is not all. Now we go on more complicated the problem, but the time is finishing. I have 2 minutes. I just show you a video and the final results of recent research. This video compare. On the upper part, you have the embedding in the geometrical space of the network. 1% link is a multi-layer perceptron. If grow at random. Down, this one is if you grow, the plot down is if you grow with the rule of link prediction. There is here the plot down on the left about accuracy, on the right, how many neurons remain in the network. So during the training, you will see that my approach learn right away a hierarchy. So the node go to the center, it means you have a hierarchy in the data, and there is a phase transition. Did you see it? From disorder to order. And after that, the video is stopped. Now we start again. Boom, there is a boost in performance. This is called the age of chaos in complex system. Most likely, we found a process in which there is age of chaos between jump from disorder to order. You have an improvement of performance. And now we need to understand what happened again as a physicist, as complex system theoretician, because if we can trigger this on demand, if we can create a network science that trigger on demand this change in connectivity that create a phase transition with age of chaos, we might really end up to create a new way to make neural network. And on the other side, we have a percolation. It means how many neurons remain. Automatically, without any parameter, the structure of the network, because of the link prediction, isolate node not useful, and by emergency of the complex system, the network shrink down to very small size. 200 neurons in the center in comparison to 1,000 or up, and the network performance is much higher. 1% of the link only. And this is an example on the article in which we show that it does not matter the type of data set or connectivity connectivity that we use. We go in ultra sparse and advantage with 1% link, where 0,0 is the performance of a fully connected network. There is a correlation of video accuracy and improvement in training speed, but only CGT do it. If you use Rigel of Google or MEST, you are in the zone of ultra sparse disadvantage. You cannot trigger performance higher than fully connected. And here we show that we can perform even with 99.9 sparsity on MLP. And the reason of this, why we can perform with 1% link only dynamic sparsity learning, because the volume shrink in an incredible way. Remember that the volume grow exponentially with the number of parameters. But the search is dynamic. So the volume change always the parameter, and this evolution, this synaptic turnover, this evolution select which link are better, which parameter are better for the gradient to go towards the minimum. So we found a better minimum. And we have now new evidence in this article where on transformers, we perform even better than fully connected transformers, and also in large language model with 70% sparsity. This is the new article. We can perform much better than fully connected large language model. So I hope that this talk was inspiring for you. This was 20 years of deep research. I didn't care of publishing. I care to understand, to go deep, and then I start to publish at the right moment things that I think are important for the society. And in my opinion, the mission that I have here is, if there are students, think bravely, don't worry, you are 24, you have all the life in front of you, create a vision and criticize what the other do. Don't have fear. This is the beginning of the revolution. When you think differently, but giving evidence, when the other don't convince you, you might find a direction that the other don't see to go on top of the mountain and then go down again to the valley and to the sea. Thank you so much. I hope this was interesting for you. I apologize. I need to go. I need to give a talk in NUS in Singapore. So I have any questions, please. This is the other article. Is a natural electronics. You can see yourself. Is on morphology. So please contact me on via email if you want to speak about these topics. It's a new field coming out because nobody before tried to use principal network science to train the connectivity of AI, but it can change the way we perform deep learning AI. Thank you so much.
Thank you, Carlo.
Bye-bye.
Bye. Bye. That comes to the end of our today's tutorial. And if anyone has some question, maybe we can discuss. And thank you for attending our tutorial, and thank you so much. And maybe you can scan this code to get the online material, and that's good. Yeah. Oh, okay. Okay. The same mistake. 他已经走了。
对，你在这上面是。
那我其实结束了，也不用勾下了啊。
你不要是。
哎，其实没有，其实可以走了呀。
也可以有QA，如果就是有一个问题的话，你可以开这个论文。
Oh, that, okay. Yeah, it can be downloaded. Okay. You can also access this page. Thank you. Also, for further discussions or possible collaborations, so we are preparing some proposal for getting the feedback So it's possible to get some level memorandum understanding. I think it's not legally the problem, but just we can collaborate in the future. That's it. So yeah, let me send it to you and you just a reply. I give you yeah, name card, right? Yeah, just send it. So yeah, who is your advisor? I mean, who's the advisor? Over network means is a traffic related issue. So we manage some of my students are working on the prediction of traffic. So in the road networks. So we are working with Hyundai company. We do know Hyundai. Yeah. So yeah, let's talk about it. Very nice. Oh yeah, sure. Yeah. Okay, this actual here. You are agents. Yeah, very well. 없어. 그런 문제가 그런 일이야. 그런 상황이 잘.
哎，刘畅，要不把你电脑
对，那我直接把它拔了吧。可以结束网络应该
应该可以结束吧？
对，应该结束吧。